All right, lecture 7 of specialist maths. We're going to look at parametric equations, and we're going to use that information to define a bunch of different relations. So some prior knowledge you'll need for this is lecture 1, which where we talked about circular functions, lecture 5, where we spoke about circles, and in lecture 6, we spoke about ellipses and hyperbolas. So there's some of the relations that we're going to be defining parametrically. Some of the key concepts that we're going to cover are parametric equations of the unit circle, parametric equation of a circle centered on the origin, then the equation of any circle, parametric equation of an ellipse, a hyperbola, and then how we can find the parametric equation of any curve. So again, I'll put timestamps on the video so you can jump to the part that's relevant for you. And if you're finding these videos interesting, please like and subscribe so that we can spread the word to as many people as possible. So let's jump into it. What we're going to first talk about is the parametric equation of a unit circle. So recall that for the unit circle, this is the relation that is satisfied. It says x squared plus y squared equals 1. And something you should hopefully know from your study of circular functions is that you can define any point on the unit circle as being cosine of the angle that's created with the positive direction of the x-axis. So what we can say is that the x coordinate is equal to cosine of that angle. So we can just call that cosine of t, where t is this new parameter that we've introduced. And similarly, y is equal to sine of t. And so hopefully pretty straightforwardly, what we could say is we can use this set notation that says, all right, it's going to be the set of pairs, ordered set of coordinates x and y that satisfy the equation x equals cosine of t and y equals sine of t, where t is an element of any real number. Or in this case, if we just think about t going between 0 and 2 pi, we'll get the whole unit circle. So inclusive of 0, but not including 2 pi. Either case, we're just going to end up going around in circles and circles, right? But the minimum domain we need would be from 0 inclusive to 2 pi, not inclusive. So what we can see here is in blue, we've actually got this unit circle, and then this point A is parametrically defined, which you can do on GeoGebra here. And this is what we usually say. We usually drop the set notation. We just say our x coordinate is equal to cosine of t, and our y coordinate is equal to sine of t. And so what we can do is we can actually play that, and we can see that that point A, again, is parametrically defined between 0 and 2 pi. 2 pi is approximately 6.28. So it's going to go up to 2 pi, and then it's going to come back. And so we can see that that point A traces out the unit circle. So that is how we parametrically define the unit circle. All right, so what we can do now is we can start to think about circles that aren't just unit circles, so don't have a radius of 1, but have a larger or smaller radius. And the way we're going to do that parametrically is we're just going to take this same idea from before, where we say sort of x equals cos of t, but now we're just going to put a parameter, another sort of parameter out the front. Shouldn't say the word parameter. We're going to put another variable, something that can change. So a, and we're going to put similarly, we're going to put that in front of sine as well. So this is going to allow us to change the radius of the circle. So you can see here we've got our unit circle again, but if I change a, that now makes the circle larger, so it has a larger radius, right? And so what we could do is we could say that if we just rearrange this, we get x on a equals cos of t and y on a equals sine of t. And then don't forget the Pythagorean identity, which says that cos squared t plus sine squared t equals 1. And so what we get is x squared on a squared plus y squared on a squared equals 1 if we substitute in cos and sine into that. So we could also say if we sort of collected, if we added these together, we would get the common denominator of a squared, multiply that to the other side, say that x squared plus y squared equals a squared, where a is the radius of the circle. Hopefully you can recall from one of the previous videos we looked at that that is the Cartesian equation of a circle. So parametrically, again, we would define it like this. In Cartesian form, we would define it like this. And obviously we can change that. A value again is the radius. So if it's 3, then the radius is 3 and so on. And you can see that point A there as being a little pesky, but let me explain what it's doing. And by that, point A is defined parametrically. So if we change that slider T, it's going to trace out that whole circle. So it's important to start to think about why this might be useful. Yeah, and why it might be relevant when we're thinking about problems later down the track, because we can parameterize these equations or these relations, and that might be useful for um, solving a whole range of problems. So that is how we parameterize a circle centered on the origin. Let's take it up another notch and say now, okay, let's just imagine we can move it left and right and up and down. So it's no longer centered on the origin. And what we're going to do here is we're going to say, all right, well, that x coordinate is now going to be defined as h plus a cos of t. And again, that h is going to move it left and right. And similarly, the y coordinate is going to get moved up and down by this value of k. So if we were to rearrange that, we would get x minus h on a equals cos of t, and y minus k on a equals sine of t, just rearranging for cos of t and sine of t. And again, recalling the Pythagorean identity, we're going to take the left-hand side here, x minus h on a all squared, because that is equal to cos of t. And so that gives us x minus h squared on a squared. Same thing over here, plus y minus k squared on a squared. And that all equals 1. Again, a is the radius of the circle, yeah? So let's put h and k to be something. Let's make h 2 and let's make k 1. So now our circle is going to be centered at 2, 1. And then if we play t, we can see that we do in fact get a circle centered at the point 2, 1, and it has a radius equal to a. A is 1 in this case. So we can see, hopefully you can see that the center of this is 2, 1, and the radius is 1. We can stop that and we can do something else just so you're confident that this all works out. Let's make a 2. So the radius now will be 2. And let's make the center 3, 1. And then if we play T, it's going to be off the screen because I didn't think about that. And you get the idea. Hopefully you can see that as that parameter T changes between 0 and 2 pi, we get a circle centered at 3, 1 with a radius equal to 2. So I think that's pretty interesting. That is the parametric equation of any circle where you've got A changing the radius and you've also got H and K changing the center of the circle. All right. Hopefully it's making some sense, and hopefully you can maybe start to think how similarly we could define the equation of an ellipse. So let's look at that. Remember, a circle is a special kind of ellipse where A and B are equal to one another. But if A and B are different, then we get an ellipse. So if we look at this, we get x equals h plus a cos t and y equals k plus b sine t. So you notice A and B are different now. If they're the same, we get a circle, but if they're different, we're going to get an ellipse. So again, rearranging this parametrically defined equation for an ellipse into Cartesian coordinates, going to get something like this. And again, recalling the Pythagorean identity and then subbing that in, we can see that we're going to get this, which hopefully you can recall is the definition of an ellipse defined in Cartesian coordinates. Okay, and then so let's just change, let's leave h and k to be 1, but let's make a and b different. So let's make b 2. And so if we play t now, we should get an ellipse. And I've made an error. All right, all fixed up. I just had my working confused. So this point A is now defined properly as x equals h plus a cos t and y equals k plus b sine t. And you'll see now when we play t, as that parameter t changes between 0 and 2 pi, we actually get an ellipse traced out. Okay, so yeah, again, this is the Cartesian form of an ellipse. This is one parametric form of an ellipse. And we'll talk about the fact that we can define a relation in multiple ways parametrically a bit later on, but this is one way to define an ellipse in parametric form. Just because we're all curious people, let's just change B. Let's change A to be 2 and B to be 1. Encourage you to pause the video, think about what's going to happen. But I think you would agree the major and the minor axes are going to change if we let T play. And you can see now that we get an ellipse that's sort of landscape, if that makes any sense. So yeah, that is the parametric equation of an ellipse with a center at 1, 1, right? Because H is 1 and K is 1. So that is how you do that. Let's have a look at the next thing, which is the parametric equation of a hyperbola. Okay, and this is a little bit more challenging. Let's again start with the sort of solution, and then we'll sort of work backwards to see that it satisfies the Cartesian equation. So let me just sort of tell you to begin with that to define a hyperbola, you're going to get x equals h plus a secant of t and y equals k plus b tan of t. Okay, if we just rearrange this, we can see that we'll get the secant of t equals x minus h on a, not b. X minus h on a equals secant of t, and y minus k on b equals tan of t. Okay, again, recall the Pythagorean identity. What we're actually going to do now is going to do a little extra step, because if you can recall from a hyperbola, it's the same as an ellipse, except you've got a minus there. What we're actually going to do is we're going to exploit an interesting fact about Pythagorean identity, and what we're going to do is we're going to divide both sides by cos squared t. So we're going to get 1 plus tan squared t, because cos squared divided by cos squared is 1. Sine squared divided by cos squared is tan squared. And then 1 divided by cos squared is just 1 on cos squared t. Okay, 1 on cos squared t is the same thing as the secant squared of t. So what this actually becomes, if we move the tan squared to the other side, we get secant squared of t minus tan squared of t equals 1. And what you'll actually notice is this satisfies the equation. Let me show you. Yeah, so we get x minus h squared on a squared minus 1 minus y minus k squared on b squared equals secant squared of t minus tan squared of t, which all equals 1. So just to sort of really drive that point home, what we've done is we've recognized that this is true. This is a true fact about trigonometric identities. It's a true trigonometric identity. And we know from our parameterization that x minus h on a equals secant of t and y minus k on b equals tan of t. So this must satisfy this equation. Okay, we have a slightly different domain for t here. And the reason it's different is because we've got cos squared t in the denominator. And we know, hopefully, from circular functions that cosine of pi on 2 is 0. And 1 divided by 0 is undefined. So we end up getting a situation where this is only going to be defined between negative pi on 2 and pi on 2, not including, and pi on 2 and 3 pi on 2, including. And I encourage you to think about unit circle again. At pi on 2, from negative pi on 2, which is down the bottom, to pi on 2, you're all good because cosine is not undefined. And then similarly, from pi on 2 to 3 pi on 2, you're fine. So let me explain it here. So negative pi on 2 to pi on 2, you're fine. And then you can't include them though. But then from pi on 2 to 3 pi on 2, you're also okay. Not inclusive. And so that should make sense when we graph it. So let's change the values of t and let's see what happens. We get this situation going on. And you'll notice that once it fully sketches out, when t approaches pi on 2, so that's around about pi on 2, so that's 1.5-ish. So when t is around 1.5-ish, the hyperbola explodes off to infinity, right? And this is where we get these asymptotes that we've spoken about in previous lectures. So we get this situation going on where we're tracing out our hyperbola. But now it's defined parametrically, right? Okay, so that's pretty cool, I think. Again, what we can say is, A and B are our dilation factors from the x-axis and the y, A is from the y-axis and B is from the x-axis. So if we do this, and we play T again, we'll see that it's been dilated by a factor of A, which is 2 in this case, from the y-axis. And you get something that looks a little bit different. So you get this. Okay, again, remember where the asymptotes would intersect is HK. So that hasn't changed now. So you get an asymptote that would kind of come along here, and then you get an asymptote that would come sort of in this direction, and they would intersect at the origin in this case. Okay, because it's fun to sort of show you this. Let's change H to be 1. And so when we parameterize that and we let T play, we would see now that the asymptotes would intersect at 1, 0. Because you get an asymptote sort of going through there, then you get one coming through there as well. So pretty interesting, I think. Yeah, that's how we parameterize a hyperbola. All right, last one. Finding the parametric equation of a curve. Okay, so let's imagine we get given a Cartesian curve, such as this one, x squared plus y squared equals 16. We do need to know a little bit about what that is so that we can parameterize it. So we know that that's hopefully a circle with a center at the origin and a radius of 4. And recall that for a circle, if you go back a few slides, that x equals a cos t and y equals a sine t, where a is the radius of the circle. So hopefully just with that information from what we learned before, we could say that x equals 4 cos t and y equals 4 sine t for t between 0 and 2 pi. But hopefully you're seeing that error there that's bugging me. Okay, I just had to change 2 pi. That should be not including 2 pi. That's the minimum domain for t, such that the whole circle is sketched out, right? Okay, so we get this as our as one way we could parameterize that circle. Now we could also parameterize it another way, and I think this is where it gets a little bit confusing. But in pink, we've actually got another way to parameterize it. We've got x equals 4 sine t and y equals 4 cos t. But now we're just going to have a different slider. So it's going to be t sub 1 between 0 and 2 pi. Okay, I don't think this should be too surprising that this also sketches out the same circle, because remember, all we need to do is check that it satisfies the Cartesian equation. Okay, so if we take x, which is 4 sine t, and sub it in there, we're going to get 4 squared sine squared t sub 1 plus 4 squared cos squared t sub 1 equals 16. So 16 sine squared t1 plus 16 cos squared t1 equals 16. And if we take 16 out as a factor and divide both sides by 16, we get sine squared t sub 1 plus cos squared t sub 1 equals 1. And we know that that's true. So we actually have 2 ways to parameterize a curve that is a circle centered on the origin with a radius of 4. So this point B is this parameterized in blue. So let's let that play. And you'll notice that starts at 0 and goes around to 2 pi. But P also just travels in a different direction. Actually starts at pi on 2. No, sorry, no. Let me think. It starts at t being 0, but because the x value is 4 sine of t, that actually starts it up here at 0, 4 rather than at 4, 0. And it actually travels in the opposite direction. So you can see that that point P travels clockwise, whereas B traveled anti-clockwise, but they both sketch out the same curve. In fact, there's I think there's infinite ways you can parameterize a curve, which makes things confusing. This is just two ways that you can do it. So hopefully you found some of that useful. Definitely worth working through a few problems and letting me know if you have any questions because it can be very challenging. So good luck, and I'll talk to you soon.